Hey guys, this is 5.3 properties of rational functions. A rational function is a function in the form of a fraction. And what we're going to do is we're going to find the domain of these functions that are fractions. And the domain is also going to tell us about vertical asymptotes, because if the denominator of the fraction cannot be 0, then what any x value that makes the denominator 0 is going to be a vertical asymptote on the graph. We are also going to talk about horizontal and oblique asymptotes. So let's start with just stating the domain of these three functions, okay? A rational function is a function of the form Rx equals Px over Qx, where P and Q are both polynomials, okay? The domain of the whole thing is the set of real numbers except any number that could make the denominator 0, okay? So for A, what would make the denominator x plus 2 equal to 0? So remember, the domain is all possible replacements for x, right? All possible values for x or replacements for x. Okay. And so we must exclude any value that would cause the denominator to equal 0. All right. So for letter A, what would make x plus 2 equal 0? And we can do it mathematically, or you could just do it in your head. So for A, x plus 2 equals 0 would be x is -2, right? Because I subtracted 2 from both sides. So our domain for A is x such that x cannot be -2. Okay. B, these are the same equation, the same function, but this is standard form. And this is the factored form. And for finding the domain, it's going to be much easier to use the factored form, right? You can kind of see why. It makes everything simpler, and it shows us what we need to exclude from either factor so that nothing equals 0 in the domain, because we're going to multiply the two factors. So this one cannot be 0. This one cannot be 0. So I'll call this one B. X minus 5 is 0, becomes x is positive 5, and x plus 5 is 0, means x would be -5. So the domain is anything where it cannot be -5 or 5. Values for x such that x cannot be -5 or +5 is our domain for this one. And then for C, we have x squared plus 1. X squared plus 1 is 0. X squared is -1. So if I want to solve for x, I need to do the square root, right? With the plus or the minus there. However, what happens if we have a square root? We did the square root because it undoes the square. So the square root of x squared is just x, but I'm left with plus or minus -1 under a radical, right? And what do we know about a negative number under a radical? That is just no solution, right? So there is no value of x that we could put here that would make this equal to 0. So we're safe to say that the domain is all real numbers. No matter what number I put here, x such that x is all real numbers. No matter what number I put here, as long as it's not an imaginary number, the denominator will not be 0. So our answers are, it cannot be -2, it cannot be -5, it cannot be 5, and it cannot, this one can be any number. I want you to see in Desmos each of these, okay? So we're gonna look at the first one. All right, our first graph is our first graph looks like this. And we said that it cannot be -2, okay? So as we approach -2 on the graph, let me zoom in, that's out. Let me zoom into -2. And you'll see that this graph gets closer and closer, but it never touches -2, right? And if I made a table for -2, -2 would be undefined for this one, okay? Our next one, it should be undefined at 5 and -5. So I'll close that one. This one should be undefined at -5. So you can see that my graph is going closer, 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 but it never touches -5. And over here at 5, we can get really close to 5, but we're not going to ever touch it. We can get really close to 5 on this side, but we're never going to touch it. So that's what that graph looks like. And then I want you to see that the factored graph looks the same. So the factored and the standard form are the same graph. All right. And our last one was 2x to the third over x squared plus 1. And we said it's all real numbers, so it should not exclude anything. Let's look at what this looks like. Good. So there's no number that is undefined. Those are all real numbers. Okay. So those are example 1. We're just practicing finding the domain. The reason we want to find the domain is because the domain tells us where the vertical asymptotes will be located on the graph. Okay, so vertical asymptotes, the graph of a rational function in lowest terms means it has been factored and simplified. If it is in lowest terms, okay? It is in lowest terms, it has been factored and simplified, has a vertical asymptote at any value that makes the denominator 0. So this is what it looks like. And this is what we saw in those graphs. At -5 and 5, it approached, but it did not touch. Okay, so the graph will not touch or cross a vertical asymptote. That's what it means, okay? The multiplicity of the factor, we know multiplicity from the last 2 lessons, the multiplicity of vertical asymptotes. If the multiplicity of the factor that yields or gives us the vertical asymptote is odd, if it is odd, the graph of the function will approach infinity, which means it's going like this, right? Will approach infinity at opposite ends. Okay. If it is even, then it will approach infinity in the same direction. So that is approaching infinity on the y-axis. Approaching infinity in the same direction on opposite sides of the vertical asymptote, okay? So they're both non-continuous because it breaks, it stops right here, right? but these are both headed towards positive infinity. So we call them that so we say that they have even multiplicity. Here, they are non-continuous and they are both headed toward infinity, but one is toward positive infinity and one is toward negative infinity. So we call that an odd multiplicity. Okay. All right, so for example, an even multiplicity might be the equation, the function f of x is x over x minus 1 squared. So the multiplicity is even because 2 is even. This 2 is even. And so when we put this in Desmos, we see that the graph is going up towards positive infinity forever. Okay. And then an odd multiplicity might be x, f of x is x over x minus 3. Here, it's an understood 1, right? 1 is even. So at -3, at +3, we're going to have 1 going towards negative infinity and 1 going towards positive infinity forever. All right, so that is what is meant by the vertical asymptote. And just to be clear, the vertical asymptote is a line where the denominator is 0. So it is where the domain is excluded. Okay, those are the vertical asymptotes. Let's find some vertical asymptotes. Verify using a graphing utility. So basically we want to factor, we want to simplify, we want to find the domain of each of these, okay? So I'm going to start down here. For A, we have x minus 3 in the denominator. I want to find the domain. So we cannot simplify, right? It said in lowest terms, okay? So check that you cannot factor or simplify it. We cannot factor or simplify x minus 3. The vertical asymptote will equal the domain, okay? The domain is excludes any value that sets the denominator equal to 0, okay? So the domain here of x minus 3 would be x such that x cannot equal 3, right? So our vertical asymptote is at x equals 3. The vertical asymptote is where the domain cannot be, okay? This x minus 3 has a multiplicity of 1. 1 is odd. So it's approaching from opposite directions. We should have a vertical asymptote at x equals 3, and the vertical asymptote should approach from opposite directions. Let's check. Done with these two. So here's our first graph. Right at, it's getting closer to 3. Let's look at our table. At 3, we are undefined, okay? And it is approaching from opposite directions. Okay, let's go to B. What would our domain be for b? Ooh, b we can simplify, look at that. So x over x squared minus 49. Again, this is the difference of two squares. So that can become x over the factored form. The factored form of x squared minus 49 is x plus 7 times the quantity x minus 7. Okay? So this is factored into a sum and a difference so that we can exclude two things from the domain, right? So now the domain x such that x cannot be -7 or +7, right? Those would both set this equal to 0. So our vertical asymptote is at -7 and another one is at 7. They are both odd. Or sorry, they both have a multiplicity of 1. One is odd, so they will approach in opposite directions. At both -7 and 7. Let's check. So here is -7 is undefined and 7 is undefined. They're approaching from opposite sides. All right. Letter C, x squared over x squared plus 9. So we can factor this. So we have f of x equals x over x squared plus 9, but we cannot simply reduce this because the denominator has a plus. When it has a minus, it's the difference of two squares, but when it has a plus, it cannot be the difference of two squares. So we try to solve it for x, right? We set it equal to 0. X squared plus 9 equals 0. X squared equals -9. So I need to square root so that the square root of x squared becomes x. Now we have x equals plus or minus the square root of -9. However, the negative under the radical is no solution, right? So we have no solution that gives us a 0 in the denominator. So this is no solution. So the domain is x such that x is all real numbers, which means there are no vertical asymptotes. Let's check. Close that one. No vertical asymptotes. It goes forever to -infinity and infinity on x, but there are no vertical asymptotes on y. All right. Letter D is, I'll rewrite it since I've gone off screen. D is g of x is x squared minus 25 over x squared plus 2x minus 35. Okay. This one we can actually factor. So this is the difference of two squares. So that becomes the square root of x squared, which is x, and the square root of 25, which is 5. So we have the plus 5 and the minus 5. Here you have 35 and 2. So that just factors to x plus 5 and x minus 7, right? X times x is x squared. X times -7 is -7x. X times 5 is 5x. Oh, sorry. +7, -5. So that will be +7x minus 5x, which will give me 2x, and then -5 times +7 will give me -35. So if I factor it out, I know my domain is x such that x cannot be -7 or 5. Okay? But remember we said the vertical asymptotes are only after it is reduced as much as possible, simplified as much as possible. Is there a way to simplify this? There is, so I'm going to rewrite it. X plus 5 times quantity x minus 5 over x plus 7 times the quantity x minus 5. So you see that these are being multiplied and that we can cancel out a factor on both the top and the bottom. So now when I'm finding my vertical asymptote, I only need to count the -7. There's a vertical asymptote at -7. It is a multiplicity of 1, so it is odd. So they're going in opposite directions. All right, so you might be asking, well, let's show this on Desmos. So here's our graph on Desmos. And you might be asking if the domain includes that it cannot be, x cannot be 5, why wouldn't there be a vertical asymptote at 5? And it's because we can only find the asymptotes after they are simplified. However, you can see that at 5, it is undefined. So right here on this graph, at x equals 5, hold on. All right, sorry. I think that because I set up that chart, you couldn't let me. Okay, so as you approach 5 with my mouse, 4.8, 4.9, 5 is undefined, and you can't really tell because of my cursor here, but it's an empty circle. So there is no point there. And on here, 5 is undefined. So it's not a vertical asymptote, but it is a hole in the graph. So just so that is clear. So we found all vertical asymptotes and we proved it using our tracking utility. The next one is horizontal. So vertical is always up and down. Horizontal would just be this way. And oh, sorry. Horizontal would be left to right. And then oblique would be slanted. Slanted along a line of y equals mx plus b. Okay, so there are many different horizontal or oblique asymptotes, and there are rules for how to decide whether it has a horizontal asymptote or an oblique asymptote or neither. Okay. The first one, if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is at y equals 0. Okay. If the degree of the numerator is equal to the degree of the denominator, there is a horizontal asymptote at y equals the leading coefficient of the numerator over the leading coefficient of the denominator. If the degree of the numerator is equal to the degree of the denominator plus 1, then it has an oblique asymptote at y equals ax plus b or mx plus b. And then if the degree of the numerator is greater than or equal to the degree of the denominator plus 2, there will not be any horizontal or oblique asymptotes. Okay, so it all depends on the degree of n, the numerator and the denominator, and the degree is the largest exponent, right? So it depends on the degree, and the degree is the largest exponent. Okay. A vertical asymptote means the graph cannot touch it or cross it, but the graph can touch or cross a horizontal asymptote or an oblique asymptote. It just describes the end behavior of the graph a little bit. Okay, so I would write this a different way. This is how I would explain these 4 points right here. I would say there is a horizontal asymptote at y equals 0 if, so we have the numerator over the denominator, right? So the numerator's degree is less than the denominator's degree. If the numerator's degree is less than the degree of the denominator, we have a horizontal asymptote at y equals 0. If we have a horizontal asymptote at the leading coefficient of the numerator over the leading coefficient of the denominator, it is because the degree of the numerator is equal to the degree of the denominator. Okay. If we have an oblique asymptote at a equals mx plus b, or sorry, y equals ax plus b, or y equals mx plus b, that is because the degree of the numerator is equal to the degree of the denominator plus 1. Okay. And lastly, we have none when the degree of the numerator is greater than or equal to the degree of the denominator plus 2. All right, let's practice this. So find the horizontal or oblique asymptote if one exists and verify using a graphing utility. So we need to look at the degree of the numerator and the degree of the denominator, and that's the biggest one, right? So I'm just going to highlight those right now. We have a 4 and a 6, right? Here we have a 3 and a 2. Here we have a 2 and a 2. And here we have a 5 and a 3. Okay, so that's what we're looking for because we're deciding whether it has a horizontal or oblique asymptote based on the degree of the numerator and the degree of the denominator. So our first one, analyze degrees, decide which of these it matches best, okay? Our first one is 4 and 6, okay? 4, 6. So the numerator of the degree of the numerator is 4. The degree of the denominator is 6, right? Would we say that that is 4 is less than 6, 4 is equal to 6, 4 is equal to 6 plus 1, or 4 is greater than or equal to 6 plus 2, okay? It's 4 is less than 6, right? So that means we have a horizontal asymptote at y equals 0. Let's look. That's the correct graph. All right, a horizontal asymptote at y equals 0 means the end behavior moves to negative and positive infinity on the x and approaches 0. Okay, so that is correct. This is y equals 0 and it is approaching 0. All right, our next one, we have a 3 and a 2, right? So this is 3, this is 2. 3 is less than 2, 3 is equal to 2, 3 is equal to 2 plus 1, or 3 is greater than or equal to 2 plus 2. It's this one, right? It's a 3 is equal to 2 plus 1. 3 is equal to 2 plus 1. So that means we have an oblique asymptote at y equals mx plus b. But now we have to find what mx plus b is, okay? And the way that we do what our equation is that they are, that the asymptote is on, okay? And to do that, we have to divide 2x to the third plus 3x squared plus 2 by x squared plus x plus 1, okay? So let's do that down here. So I have x squared plus x plus 1, and then I have 2x to the third plus 3x squared plus, I'm going to put a placeholder here, right, for the x's. 0 plus 2. You can even put 0x plus 2. Yeah, okay. So if I want this divided by this, what would I multiply this by to get 2x to the third, right? 2x to the third divided by x squared would give me 2x, right? So if I multiply all of this by 2x, I would get 2x to the third plus 2x squared plus 2x, right? And then I have to subtract all of that, remember. So we're going to subtract all of this. So I'm going to change all of those signs. So that becomes 2x to the third minus 2x to the third, they cancel. Plus 3x squared, sorry, that 2, I tried to write a 2 and it didn't work. 3x squared minus 2x squared is just x squared. And then x0 minus 2x would just be negative 2x, right? Okay, my next term is x squared. X squared divided by x squared would just give me 1. Positive 1, so I have 2x plus 1. X times, sorry, x squared times 1 is just x squared. X times 1 is just positive x, and then 1 is just 1. And then I need to subtract that. But you know what? I'm just looking for y equals mx plus b, and I already have that. So I can actually stop right here. I should bring down that too. But I can stop right here because I already have 2x plus 1. So instead of y equals mx plus b, I'm going to say it's y equals 2x plus 1. Okay, let's see if we are correct. So that is this graph, not that one. And is the end behavior following the line y equals 2x plus 1? Let's find out. Y equals 2x plus 1. Are we following that line? And I would say yes, we are. All right. So I know division is not easy, but at least you can stop. You can stop as soon as you get 2 terms. Okay, so for this one, we have 2 and 2. Of our choices, 2 is less than 2, 2 is equal to 2, 2 is equal to 2 plus 1, or 2 is greater than or equal to 2 plus 2. It's this one, right? So we have a horizontal asymptote at the leading coefficient of the numerator over the leading coefficient of the denominator. Oops, sorry. I'm going to put an N and a D because those look too similar to me. So the leading coefficient is the number 9. It's the number that is with the letter of the leading term. And then it's over 3. 9 divided by 3 is just 3, right? So we have a horizontal asymptote at y equals 3. That should say equal y. So let's look here. We're done with this one. We're going to look at this one. Ooh. So remember, we're not worried about our vertical asymptotes, but is this close to the line y equals 3? It is. It's staying very close to y equals 3 on both the negative and positive x values. All right, so that one works. And then our last one is the number 3, or sorry, the number 5 and the number 3. So we had 2 is equal to 2. Now we have 5 and 3. Which one of these does 5 and 3 fit? 5 is less than 3, 5 is equal to 3, 5 is equal to 3 plus 1, or 5 is greater than or equal to 3 plus 2. It's this one, right? 5 is equal to 3 plus 2. So there is no horizontal nor oblique asymptote. 5 is greater than or equal to 3 plus 2. No asymptote. There's no line, no height to describe what is happening mathematically. No horizontal nor oblique asymptote. Okay. We cannot describe what is happening mathematically with a line. Let's look at Desmos. Very hard to see, but you can tell that it's not following any line on the horizontal axis. And that is the end of 5.3. Thank you so much, and I will see you next time.